To get done for the art. That involves like 2 or 3 intros plus all our interviews, which is gonna take.
One. One.
That would have been
questions like regarding projects, test, whatever.
Okay.
So I did the project and I was wondering if we're allowed to use like functions in the string library, like
Yeah.
token.
Yeah, if you want. So I don't necessarily recommend it. Like the STRT, okay, but if you want to use it, you can use it.
No, it's just because like
It's annoying to use. Right.
Oh, yeah, because I figured it out.
Yeah. I mean, it's fine. Yeah.
Okay, and are we allowed to use those kind of functions on tests if we know how to use?
So that depends on the question. So the question will say what you're allowed and not allowed to use.
But if it doesn't say.
Yeah. Yeah.
And
I mean, a lot of the time it will say like in the Python one that like in Python it said like you're only allowed to import now. Something like that.
so
Yeah, so you could have like string a string which would include strT, okay. Like the thing of it is that most people who attempt to use strT, okay on the test, in my experience, just don't do it well. Yeah,
because like you have to like next time.
Yeah, it's like easy to make mistakes. So yeah.
And I guess like in the project I saw that you can only submit your autocomplete.c.
That's right.
So when we need a free memory, which is in the main,
We'll free it for you when possible. So when possible, you should free it. If you malloc something that you can free, then you should free it. but when not, then we'll do it for you.
Yeah, it's like something like the entire list, like.
And so, yeah, I mean, you are creating something that you're not supposed to create. So, if that's the situation, obviously we'll complete it for you. We know what to expect. Okay, yeah.
And I saw that in the header file they use like if not define. Is it okay if we use if and def? Because
Yeah, that's the same. Yeah.
okay, cool. And finally, like, do we get like an age sheet for midterms?
I'll think about it. I'll announce it when I know.
Okay,
yeah.
cool. Thank you.
Already tried it. Like this kind of cello, cello. Yeah, that makes sense. Yeah. Hey. Hey. Okay. Hi. Hello, everyone. Just kind of administrative stuff. Currently the winning vote for the optional agentic AI coding studio is Monday. I am not sure I can actually book something for Monday because the university is closed. So if I can, then it will be on Monday and I'll announce that. If not, then maybe Sunday. So there will be office hours, from basically tomorrow until Wednesday next week, more or less every day to support the midterm, the project, stuff like that. I am away from Thursday to like Sunday afternoon next week, not this week, next week. But we'll do something online. We'll send some TAs. It's going to be fine. So I won't announce the agentic AI thing until like probably tomorrow. It looks like Monday is winning, but if you have other preferences, then make your voice heard. Maybe we'll decide to do it on Tuesday instead, and then there's not going to be problems with booking. I might decide to do it anyways if I cannot actually book for Monday. Come, it's gonna be fun. I can't promise anything in particular. I've never tried running something like that before, obviously because those tools didn't exist until quite recently. So we'll see how it goes. I emailed so that the studio, if you haven't clicked the link, it's based on this course at Brown that some colleagues are running. So they're running it as a full course with a prerequisite that's basically something like 180. They're allowing students from other courses as well. I asked them, they said that they didn't really see a difference between at least the students who came to that studio, who came with just kind of a 180 like prerequisite, and more advanced students in terms of kind of how fast they're doing projects, stuff like that. So I think it should be good, but it's going to be an experiment, which is why I'm not doing it as a lab. I'm just doing it as an optional thing. If you want to come, you can come. If not, then not. Completely up to you. It's not going to be tested or anything like that, unless I decide that it went so well that they do like a lab about it in the second half of the semester. So the way it's going to go, I think, is if you look at the projects that have been assigned there, obviously they're assigned as homework there. We are going to do it more like a hackathon style where I'll book like, I don't know, like 4, 5, 6 hours, something like that. We'll see what works. And we'll work on just, the first few assignments there. The assignments don't really take that long. So what I'm told is every assignment for students takes like 20 minutes to do, at least like the initial prototype. and then people build out from there. So there's like students testing each other's code, stuff like that. So that takes time. So we'll see. It's going to be a little bit of a mess, but it hopefully could be fun. I also think that I don't know to what extent people have starting doing their praxis projects up to now. I suspect not to a very large extent. But what I see from last what I see from last year is that actually a lot of praxis projects end up doing something like at least a vibe coded component, depending on what exactly people do. Of course, like not everyone, and then not everyone in the team is responsible for that, but I think it's good. And I think that's, at least partly that is how people are going to write code. So we might as well find out. Okay, so this is that. Again, if you have scheduling preferences, vote now or forever hold your peace. So the plan for today is to basically do more examples of the kinds of things that we had done last week. And then the lab, I hope is going to be easy because it's literally just do whatever it is that I'm about to do now in front of you from scratch. So you can hopefully do it fast or you can do it slow, but make sure that you do it from scratch, because if you look at past midterms, like that's the kind of thing that I sometimes ask. So you want to be able to do it from scratch. And then you can work on project one, whatever. So it's not supposed to be an extremely challenging lab because I'm giving out the answers more or less ahead of time. So here's what I'm going to be trying to do. So if you remember, we started talking about abstract data types last time, and we said in a way MyString was an abstract data type in the sense that we're saying, well, what's a MyString? Well, it's a buffer and it has some operations that are associated with it. The way they are written down, if we're implementing them in C, is with this .h file. Right? So that's a specific decision about how the buffer is stored. And then you have functions that operate on the string. All right. So what I want to do is, again, the same kind of thing, but with a different data structure. So it has various names, but a lot of the time, if you program in Java, it's literally going to be called array list. If you program in Python, it's kind of like a list, except the list can be heterogeneous. We are going to make it be a homogeneous list, so only integers allowed. And we want it to be resizable. So what do we mean by this? So a sequence of elements that are integers. So we'll say a sequence of integers. And we say that we want to be able to append an element, insert an integer at a specific index, delete an integer at a specific index, and get the integer at a specific index. So that's basically like the square bracket operator, right? So we want to be able to do all of that. So that's not something that you can do with just a plain C array. For one, because with an array list, you want to be able to append as many as you want. With an array in C, it's fixed size. You cannot resize it. So the aspect of it that's called being dynamic, that's important. Want to be able to append as many times as you want. And then stuff like deleting an integer, stuff like that, you could imagine implementing it, but stuff like inserting, again, requires that you possibly rejig how the data is actually stored in the thing. Okay. So that's what you want. So the way I would start implementing is I would say, okay, how am I gonna use it? Well, I'm gonna say I want to declare an array list. So here I'll do it with this kind of initialization. In the lab, you're gonna do it the other way. So I want to say create list. And maybe I want to be able to send some initial values. Okay, and that initializes the list to have 6, 7 as the contents. And then I want to be able to say append L8. And that's supposed to make it so that L is now 6, 7, 8. And so on. What else do we want to do? So you want to insert. So insert, as in Python, we want to insert before the index, right? So if I say insert 9 before 0, so this is basically prepend. And this is going to be like 12. So L is now going to be 12, 6, 7, 8. So the same idea as in Python. I should say append list, insert list, so that this is just a convention so that like they all have the same names or whatever. Make sense? So I want to be able to do stuff like that. So unlike with strings, where we kind of had the cheat of being able to say, I'll just print f with %s. Here, like it's nice to just have a function that prints the list. And that's gonna print the contents of the list L. Okay, so that's the kind of thing that we want. Yeah. Yes, I did not say L. Thank you. Okay. All right. Okay. So that's the kind of thing that I want. So I'll just implement that and we'll see what I need for that. So this is going to be I'll save it as ArrayList.c. And I'll open folder. Okay, we're over here. So CPP ordinarily stands for C++. That was just like the default name. Just delete it. Yes. Okay, and we are over here. So I'll rename it to like array, like use array list or something, because that's like the main. And now I'll define my array list.h. So this is just the usual header guard, right? So I'm saying if it's not defined, then define. This is endif. This for me. Yes, it is for me. Is there a 9 in the insert list? Okay, I don't know. I'll check it out. So I'm saving it as ArrayList.h. There was a 9 somewhere. So it's 12. Sorry, I don't know what it. I have no idea what this is. Okay, so insert list. So L, what they there shouldn't be a 9. That was. Oh, I don't know how that happened. Thank you. So okay. So we are defining the array list like this. So we need to have some kind of structure. Maybe we'll modify it later. So presumably you need a buffer of integers that will allocate later. And similarly to the string, we'll have a size and we'll have a capacity. So size would be how many numbers are stored currently, and capacity is how many can we store overall. Hi, Chris. Okay. And we'll name this array list. Okay. So, okay, all right. So now we want to just define the prototype for all those functions. So we want create list, we want append list, and we want insert list. So what would that look like? Well, it doesn't return anything. So it would be like void and then create list takes in a pointer to the initial array, and it takes in the size of the initial array. You have to do the size of the initial array because this is only the address of the first element. You need to know how many elements. This is not void because it actually returns a list like so. Right? Because we want to use it, sorry, for switching in this implementation, unlike with the lab that you're about to do today or on Wednesday, here you actually want to return the array list. This is as opposed to passing the address of array list star L. So that is also possible. So, okay. It's like that. So append really is void, and that takes a pointer to array list. And it takes an lm that you want to append. Okay. And then here we have insert list. Again, you have array list L. Just, yeah. And this would be the index. And this would be lm. So that's like this. Array list is defined like this. And now you want to also define array list C, which will actually implement all of those functions. So I'll save it as ArrayList.c. And I'll copy and paste all of this stuff so that they can see it. And I'll start working on it. So I'll include ArrayList.h. I'll include stdlib.h because I need my malloc. And I'll include stdio.h because I need to print stuff out. All right, so let's define this guy. So what do I need to do? I need to say I'm creating an array list. And initially it's nothing. Some people just don't want for undefined values to ever be there, which is a reasonable thing. They just say equals 0 right away so that nobody tries to access L before it's ready. You can also just malloc it right away. Let's do that. This would be malloc, and this would be size of array list, like so. So that is now ready. You now want to say, okay, now that it's allocated, I can set the size and the capacity. So the size is just going to be the size that got sent. And the capacity is going to be the same thing because that's just what we allocated. So the reason you're doing it like that is that if you delete an element, the size goes down, but the capacity stays the same. Make sense? So capacity is how many you can put there. A size is how many are there currently. So finally, we want to copy from init to the buffer. Before we can do it, we need to actually create the buffer. Right. So this would be int star, and that's because they're all integers. And this is this much. If you want to be like really strict about it, you might say, I'll just make sure to malloc. Of course, they're equal anyway, but exactly L capacity. That makes it so that it's consistent. Of course, it was consistent before as well. Make sense? So, okay. Everything's allocated. We can now copy the contents, which we'll do now. There is a faster way of typing it, not necessarily a faster way of implementing it, that you'll do in the lab using memcpy, the library function. So this is going to be L buffer I is init I. Those are, there's no nulls at the end there or anything like that. It's just a block of integers. And how many of those integers are, well, this many. After we're done doing all of that, we'll return L. Make sense? So let's do kind of a symmetric function to that, which is you can create list. Let's try to print it. So that's going to be array list L. And we'll say for I equals 0, I smaller than L the size. So not the capacity, the size, because it might be that the capacity is greater. And we'll print L buffer I. So if we want to be nice about it, we will maybe print it with spaces or something. Like this. And then after we're done, we're going to print a new line. All right. Semicolon. Yes. So size, I mean, like you can, right now they're equal. So when you delete an element, you can say the capacity stays the same, but size becomes smaller. So this is like the number of elements stored. And then this is like num of elements that can be stored. So maybe not necessarily every time, but usually. But when I remove the element, I can choose to also change the capacity, but I can choose, and I will in fact choose not to change the capacity when deleting an element. So that would be one way in which it's going to create itself. But you can choose to shrink and expand it every time you either add or remove, in which case, yeah, this is superfluous. So whether it's more or less taxing is something that you can explore. It depends on how exactly you use it, right? So if what you expect is that mostly you're going to be appending and then you're going to be deleting not very many times, then the time that you spend resizing the array is not worth it in terms of the savings and space that you get. If you expect to, like, maybe it expands a lot and then it shrinks a lot and then expands a lot again, at that point you might consider shrinking it. What people usually do, and that's what's going to be suggested in the lab, is that you do exponential growth and exponential decay so that you increase the capacity by a factor of 2 every time when you need to. And you also decrease the capacity by a factor of 2 when you can. So when you're using less than half the capacity, then you change the capacity. What's best is kind of depends on the application. So it like depends on the frequency of append and delete operations. Yeah. So like very often, right, if you think about the Python programs that we wrote so far, like we don't delete elements very often, right? So it would make sense that you wouldn't necessarily shrink the array every time you delete. Okay. So that's like this. So we haven't talked about freeing yet, but let's use the array a little bit. So here we're saying array list, and we'll create this array. Append is not there yet, but we now have a print list. And if we include array list, we are about ready. So at this point, we have to go and configure the compilation task. Wait for a bit. We are over here, and we'll say, I want to use array list C. And I want to say array list C. Again, kind of the rule of thumb is list the C files that are relevant. Do not list the H files. It's going to be fine that way. Okay. So let's try it. All right. And what we see in the terminal is that we indeed managed to print 6, 7. Okay, so basically kind of what we did is implemented the Python functionality of like saying L is the list 6, 7, and then print L, right? And like a lot of what we do in C is basically saying like, let's do what we could do in Python, but in C so that we know the details of how it's implemented. And then actually the discussion with you here is relevant. C gives you the flexibility of changing the implementation so that you can do it faster in principle. Here, there is not like really a universal way of doing it faster, but there is a way of doing it faster for some circumstances when you know that you're like appending often, but deleting not as often, stuff like that. Okay. Let's do an append. So this is missing a semicolon. So append requires a new thing because it might be that you're out of capacity. So this is going to be append list. It's going to take array list cell. Did we say int index? Yeah. And lm like this. And let's say that we want for this to always work if we can make it work. So what C provides you is realloc. And that return, and then of course, like the size. So that returns a block of memory that can store n times size off. Bytes. It could be the same block. So it could just say, just keep writing to the same block. It's fine. Like that you thought there was no space there. That's just accounting. We'll just expand it. It's fine. Just keep writing there. Or it could say, I'm returning a new pointer. If you write at the end of your current block, there is like other stuff there that you kind of just replace. Okay, so that's a way to resize. So that's what it'll do. So we'll say, first of all, is that an issue? So if the capacity is the same as the size, then yeah, it's an issue. You need to increase the capacity. So we'll say, okay, I want to increase the capacity, let's say by a factor of 2. And what I'll say is I want for the buffer to be an int, and this is going to be realloc. That's going to be the current buffer. And then you have size of int. And you have the new capacity, like so. Oh, that's right. Okay. So, okay. So the good thing is it could be the same block, in which case it's not very expensive computationally. If it's not the same block, it'll handle copying the data for you from the old block to the new block so that you can use the new L buffer as the contents of the array. If that didn't happen, then it doesn't matter. And we just say L buffer L size. So it so far has been all stored from 0 up to size -1. So now we want to store it at L size. And that's going to be equal to LM. If you want to be fancy, you can say L size ++. So that's going to work. It's going to increase L size, but only after you assigned LM to L size. If you don't want to be fancy about it, you can just say L size plus plus over here. That's the same. I generally prefer not to save one line of code in order to have like a 20% probability of confusing myself. So I'll usually write it like this unless I'm really tempted. Okay. So the idea is if the capacity was too small, increase the capacity using realloc, like so. And then just put the element at the end. Let's test it. Okay, so we have our append list over here. Oh no. Okay, append list with type for array array list until m. Previous public declaration. Okay, so array list. Append list, append list, append list until m. Append list. Okay, so it thinks that there is conflicting types. So IDX LM. Oh, because I don't need the IDX. That's right. So I never used it. So that was just like a confusing thing. All right. So that was the issue, is that it was supposed to be this. It had an extra int IDX for no reason. So okay. That should now work. And here we are. So we now have 6, 7, 8. Imagine. Amazing. All right. So let's do something that's kind of more difficult. Delete list, I guess it was called. We didn't actually do a delete. Okay, we'll do an insert then. So this would be into dx. This is allowed until m. And we want to insert lm after index ID, after index IDX. We have the exact same thing as before, where we might need to increase the capacity. So now what we want to do is we've increased the capacity. So imagine that the situation is like this. So the elements are like 5, 6, 7. And we want to insert the element after index IDX. So instead of the 5, basically. So that means that we want to put the element over here. And that means that we want to shift all of this here so that there is space for this index. Right? So one way to shift in the lab, you'll look up the library function to do it. But one way to shift is just a for loop. So I'm just going to say, and I'm going to say for I is IDX plus 1. I is smaller than L size I plus plus. So basically everything that needs to be shifted to the right starts at IDX plus 1. So Actually, technically, we said like after IDX, so we start, I guess, with just IDX. And we'll just move it one space to the right. So like the moving is kind of annoying because if you're doing it that way, if you're overwriting L buffer I+1 with this, then you lost information there. So there's nothing to overwrite later. So there's multiple ways of fixing it. I think the way I'll fix it is I'll just actually go from the end to the beginning so that it's not a problem. So I'll just say the last thing that I'm copying is going to be is going to be 0, is going to be 1, and then the first thing is this guy. And now I'll just say, okay, so L buffer at this guy is equal to L buffer at this guy. And that way I'm writing to L buffer at I for the first time. That didn't have anything there, so that's fine. And then I'm writing to L buffer I-1, and then I'm writing to L buffer I-2, and so on. And the last thing that I'm doing is I'm moving the I'm moving the I equals to IDX, which is what I want to make space for. So once I made space for L buffer at IDX, I can put the LM there. Makes sense? So there is a library function that lets you get away with not doing this annoying thing, which you will look up either right now or Wednesday noon. All right. So now that we've done that, we can do like an insert list. Okay. Hopefully it works. No such luck. That's just because no semicolon. All right. So there was one bug, which is that I wrote everything. Does anyone see the bug? Hint 3.7. Yeah. Yeah, exactly. So I inserted the element, but here I increased the size so that when I printed all 3 at the time elements. Here I increased the capacity, but I wrote 4 elements, but I never said that there are actually 4 elements. So I'll say size plus plus. Like so. So now, like what I wanted is 12, 6, 7, 8. And that is what I shall get. All right. Okay, so that's like this. One more thing that we need. So since we've been malloking, we also need to free stuff. So when you realloc, if you move the block, the free is taken care of you for you behind the scenes. So that's fine. But we need to be able to free the list. So we'll name it like destroy list, and that's going to be array list L. And that's going to work the same way that create list works, except in the other direction. So when you are creating the list, you are allocating the buffer, and you're also creating space to store the address of the buffer and the size and the capacity. So when you're freeing, you got to do it in the other order. So you got to first free the buffer because you need to be able to access the buffer. And then once you free the buffer, you can free the list L itself, which contains, the three numbers, the address of the buffer, and the size and the capacity. So this would be free buffer and free L. All right. So that's not going to affect the output. It's just going to make it so that Valgrind doesn't complain. So I'll say destroy list L like so. I forgot to include it. So it kind of ran, but I forgot to include it in array list.h. So it sometimes would compile, sometimes would not compile, depending on exactly like the order of the order in which the C files are put to GCC. But the good thing to do is to actually just take this signature and put it in array list.h so that there is no confusion. Okay, and now it ran without warnings. And we can run Valgrind on it as well and say use array list like so. So this is the name of the program. So usually the name of the program by default is just going to be the name of the C file, but without the .c on Linux and Mac, .exe on Windows. You can also see it if you go to the Explorer tab. So this is the program. We'll run it with Valgrind. And here we see that everything is good. All right. The last thing that you're going to be asked to do in the lab before you start working on project 1 is kind of do this kind of thing with another custom array list, which is honestly not very different from the one that they used here. And just swap a different array list.c for it. So for example, you might imagine that instead of multiplying the capacity by 2 when you're inserting, you are adding 1 to the capacity. That would also work. It's just a question of a trade-off of how often do you malloc versus how big is the malloc that you're doing. Does it waste space? So you can do it like this. So by itself, running this is not going to change anything at all because you're still running, use array list with array list.c. But you can go to, terminal configure tasks. And then here you would say something like use array list.c and also array list 2.c. And then you can run it with the new file. The idea is that the outputs are going to be the same, but if you measure the speed or you measure the memory usage or something like that, that might now be different. And you can see that it worked because if you scroll, so if you change to this tab, I guess, it was GCC, and then we compiled use array list with array list2.c. So when you're experimenting with it, or like when we autograde your assignment, that's exactly what we do, right? Is we take your autocomplete.c and then we compile it with our stuff. All right. Questions about any of that? Yeah. Sorry, I cannot hear you. So the difference is literally the one line. So in array list, I had 2 times this. In array list 2, I make the new capacity be the old capacity plus 1. Right, so it's like an implementation trade-off of how much space you use versus maybe you save a little bit of time for not malloking every time. Yeah, bye.